So in kinetics, we talked about how fast it takes us to get from the start of the reaction to some point. And in reality, most reactions don't go all the way to completion, right? You don't end up with all products and none of the reactants. And so we described the starting point. Equilibrium is describing the end point. So we're going to end up with some balance of products and reactants, and that's what the equilibrium is. Rates tie into that. Rates tie into that, but it's a different thing. The rules change, or the conditions change as you approach equilibrium. All right, so the kinetics was the speed of the reaction. The extent of a reaction is governed by thermodynamics, which we will talk about later. And chemical equilibrium is sort of our first look at those thermodynamics, but talking about it really in more practical terms than the sort of theoretical terms. The equilibrium constant, which I know is just great, is also K. So it's different from the rate constant. Specifically, the rate constant only takes into account your reactants and how much of your reactants you have. The equilibrium constant takes into account how much of your reactants and products you have. So that's what I'm saying. This is at sort of the end point of our reaction rather than the initial point. Because at the initial point, we didn't have any products to speak of. So going to the other end, our new K here, and it'll usually be K, or we'll have Kc, and we'll talk about Kp as well, one for concentration, one for pressure. And K really is a ratio of how many products we get compared to how many reactants we get. So if you have a really large K, that means you have a higher proportion of products than you do reactants. If you have a really small K, then you have a higher proportion of reactants than you do products. And these are, well, this is actually chapter 18. We'll talk more about the magnitude of equilibrium constants. So one place where you see this happen is in red blood cells, which contain a protein that you've probably heard of called hemoglobin. Right? That's what picks up oxygen in our lungs, carries it to your, well, everything. And the double arrows here are indicating that it's, the reaction can occur either in the forward or the reverse direction. So that's our chemical equilibrium, right? We've got flowing both ways. And the concentrations of the reactants and products in an equilibrium reaction are described by equilibrium constant K, again. Big K, lots of products. Small K, not very much products, lots of reactants. And equilibrium systems, and this is why hemoglobin works, equilibrium systems respond to changes in ways that maintain equilibrium. So they always want to have that sort of preferred, they give it a preferred balance of reactants versus products. So if you add more products, they'll decrease the amount of products, increase the amount of reactants. For hemoglobin, it's transporting oxygen, so it needs to be able to pick up oxygen in your lungs and deliver it to oxygen-deprived tissues. And it does that by taking advantage of the equilibrium of hemoglobin, oxygenated hemoglobin and unoxygenated hemoglobin, where in your lungs, there's a high concentration of oxygen, so that adds to the O2 concentration, so it pushes this reaction to the right. And so most of the hemoglobin, when it gets to your lungs, saturates with oxygen. Right? All becomes the oxygenated form of hemoglobin. Then as it travels through your body and gets to your muscles, to your brain, to other tissues, the oxygen concentration in those parts of your body are going to be much, much lower than your lungs. And so this equilibrium, well, the equilibrium stays the same, but the balance shifts. So now as they're traveling, that concentration's dropping. And as that drops, the concentration of oxygen drops. The hemoglobin also starts to drop its oxygen and deliver it to your tissues. Oops. Okay, get out of here. This goes even another step with babies, unborn babies. Unborn babies have fetal hemoglobin, which is a modified version of hemoglobin that has a higher, larger K. So it'll load oxygen at lower concentrations of oxygen. So even though the mother's blood and the baby's blood don't actually mix, that contact point, the fetal hemoglobin has a higher affinity for the oxygen than the mother's hemoglobin. And so that hemoglobin, or that oxygen, gets transferred from the mother's hemoglobin to the fetal hemoglobin. Then that gets carried into the baby, where it deposits the oxygen to oxygenate the baby's tissues. So you've got like an equilibrium feeding into another equilibrium. And that has to be the case, right? Because otherwise the blood that's getting there is already going to be lower in oxygen than when it came from the lungs. So it has to still be able to deliver that to the baby. And so we covered this with rates, reaction rates. As we increase our reactant concentration, we also increase the rate of that reaction. And a reversible reaction can proceed in both forward and reverse directions. So as our reactants react, that concentration drops according to the kinetics we already talked about. Then the concentration, or then the rate of the forward reaction slows down, and the rate of the reverse reaction starts to increase because its concentration is increasing. So as we form more products, we get more reverse reaction. So if you were to plot this out, let's look at these first up here. It's just these, so we got time here, right? Roughly every 15-ish minutes. We start out with just reactants, and then at just over 15 minutes, now we've got some products in there, then we've got more products, but it eventually settles into an equilibrium. And that's because the rates, or these are the concentrations. So the concentration of hydrogen and iodine, which are our reactants, start to decrease. But as they decrease, you can see the rate that they're decreasing at levels out. And for hydroiodic acid, it's doing the opposite. Its rate is the maximum. I was talking about this backwards. No. Oh, yeah. The rate that it increases is just the opposite of the rates of the hydrogen and iodine. So as it's increasing, its rate is initially at its maximum, but as we run out of reactants, its rate of sort of production slows down until they reach that midway point. Well, not really the midway point. As they reach that equilibrium point where they balance. But the concentrations here the concentrations are static, but the reactions aren't static. It's not like they've stopped. They don't reach that point and then end. It's just they're making hydroiodic acid as fast as the hydroiodic acid can break down into hydrogen and iodine. So it's like if you had two people shoveling, if you had two people who are in holes and they're shoveling dirt into each other's hole. So they're going at the same rate. So neither of them is getting any deeper, and neither of the holes is filling in, but they're tossing dirt over into the other person's hole at the same rate. So this is the key of all of equilibrium. Dynamic equilibrium for a chemical reaction is the condition in which the rate of the forward reaction equals the rate of the reverse reaction. So they're both still occurring. The concentrations don't change, but they're not necessarily equal to each other. So the relative concentrations depend on the value of the equilibrium constant. Again, that tells us what the ratio is of reactants to products. So it's like if you had two countries right next to each other. Initially, people will move from country A to country B because there's tons of space there, right? I'm going to go over there. I'm going to take advantage of all this space. As that starts to fill up, though, then country A starts to get more empty. And some of the people who initially moved to country B for all that space are going to say, hey, that house that I wanted over in country A is now available, and they move back. And then so you keep having this cycle of people moving in and out across the borders, trying to find the best place. But the amount of people in each at one point is going to be stagnant. So which statement does not generally apply to chemical reaction in dynamic equilibrium? The concentrations of the reactants and products are equal. Yes. Right, because we don't know unless we have K. Sometimes it will be. Most of the time, vast majority of the time, it's not. So the equilibrium constant follows a very nice, very convenient pattern. I like the equilibrium constant equation. It's also called the law of mass action. So our equilibrium constant, unlike our rate laws, is going to be based on the coefficients in the balanced chemical equation. So we can take our reactants, they go in the denominator, our products go in the numerator. So it's always products over reactants. And then the concentration of each is raised to the power of its coefficient. So A will be the concentration of A raised to the A power. So on and so forth for however many products or reactants that you have. So according to the law of mass action, what would be the correct expression for the equilibrium constant for 2A plus B equals 3C? Does anybody want to dispute D? No? Yeah, it's D. Because again, we'd have A raised to the second power, B raised to the first, and C raised to the third. Right? Pretty easy so far. It's a pattern. Just remember the pattern, and then you can keep applying that same pattern. So we apply the law of mass action to this balanced chemical equation. Right? We get the, again, the coefficients becoming the exponents. And we've got dinitrogen pentaoxide raised to the second, nitrogen dioxide raised to the fourth, oxygen raised to the first. So how do we express the equilibrium constant for the combustion of propane as shown by the balanced chemical equation given here? Go ahead and take a minute, write it down. Cool. Did anybody get anything else? Wonderful. Zipping right through these. So when K is large, the numerator, right, the concentrations of the products are greater than the denominator, the concentrations of the reactants. So we have more products than we have reactants. And we'll get, really, really large numbers like 1.9 times 10 to the 19, right? That is so large that the amount of reactants that you have left over is negligible, right? There's going to be practically nothing left. Anything that does go through that reverse reaction is instantly going to react again to become the products. And so then the reverse is true also if we have a small k. That means that the concentration of our reactants is much greater than the concentration of our products. And I think the one tricky thing here is remembering that negative exponents mean a small number. So this is 4.1 times 10 to the negative 31, meaning that this reaction doesn't even happen at all, right? So our reactant concentrations are so much greater than our products, it's practically zero. And again, anything that does react to form those products is going to be instantly broken down back into the reactants. However, actually, yeah, this is a great note. It says nothing about how fast the reaction goes. So this might be the case that this reaction never happens, but if you put equal concentrations into a flask, it might take a long time for it to get to that equilibrium. It'll get there eventually, and it will get there almost completely, but the equilibrium constant, the equilibrium expression says nothing about how fast. That was all kinetics. All right, so if the numerator is a large number, then, or sorry, the denominator is a large number, then your result is going to be a very small number. Right? So for K is much smaller than 1, the reverse reaction is favored, and the forward reaction does not proceed very far. If it's about equal to 1, we're talking like probably 0.5 to like 2 or 3, probably in that range. Neither direction is favored, and you're going to have pretty much equal concentrations. If K is much larger than 1, then the forward reaction is favored and proceeds essentially to completion, right? Uses up all of the reactants. So for this reaction here, we consider it's A reacting to form B, where A is the red spheres and B are the black spheres at 3 different temperatures. Which temperature is the equilibrium constant the largest? Actually, can you see that those are red, barely? I'm going to circle the black ones. How about that? So if we want a large equilibrium constant, it would be C, yeah. Because if we have a large equilibrium constant, that means we have more products than we have reactants. C has the largest number of black spheres and the smallest number of red spheres. So it's going to be the largest K value. So the equilibrium constant for the reaction A converted to B is 10. And a reaction mixture initially contains 1.1 molar A and 0.0 molar of B. Which statement is true at equilibrium? So we could write this out as the equilibrium expression. So it's going to equal the concentration of B or the concentration of A. Yeah, it'll be B. Because we can even plug in the numbers here. Concentration of, or if K is 10, well, actually, I think the easier way, if we're given, A is 0.1 and B is 1, then K is equal to 1.0. These are actually unitless, or K is unitless. 1.0 over 0.1. So 1.0 divided by 0.1 will give you 10. So B matches K, the concentrations in B. So if our chemical equation is modified, we can modify it. We can multiply the entire balanced thing by a coefficient, or we can reverse it. Then we just manipulate K with a couple rules, which are really just math rules. So the K for a forward reaction would be C to the 3, A to the first, B to the second. So what is the K for the reverse reaction? Yeah, you just flip it. You invert it. So we just, now it's C raised to the third on the bottom, and A and B squared on top. Same thing as doing K to the negative 1. K raised to the negative 1 power. So we can also multiply the coefficients by a factor. And then all we have to do is raise the equilibrium constant to the same factor. So if we take our equation on the right here, again, it's the same as the previous one. All right, so if we raise that to some power, then we're just multiplying. We're multiplying each of the coefficients by the same thing. And so we multiply the exponents by that as well. So then this is going to be C raised to the 3n, so 3 times n, over A raised to the n times B raised to the 2n. And this is useful because we can use chemical reactions, separate chemical reactions. And if we know the K values for those individual steps, we can predict what the K value would be for a combined reaction. And sometimes to make that combined reaction, you got to multiply by coefficients. You have to reverse reactions. But we'll see all that. So this third one is what happens if we add these two reactions together. Right when we did our the reaction mechanisms, right, you have to add those reaction mechanisms or those reactions together. And we can take the Ks, if we knew what the Ks are for those, and we could also add those together. Although it happens multiplicatively. So the K for the combined reaction here, actually, let's do this. So to add these two reactions together, since 2B is on both the reactant and the product side, it's going to cancel out. So the resulting reaction is just A going to 3C. So we would expect K for this, and I'll make this K3, to equal C and then raised to the third over A. And that's actually just K1 multiplied by K2. So if I do K1 is B squared over A, and then that's times K2, which is C to the third, that's a 3, C to the third over B squared. All right, so B squared cancels out. And we're left with just the concentration of C to the third over A. So you don't need to always write this out, but it's just to show you that it's the result of the combined reaction is the multiplication of the K values. So if we knew what K1 and K2 were, what those exact values were, we would just multiply them together to get the K for our combined reaction. And so we can combine all three of these steps, reversing or multiplying by coefficients, to calculate for, or to calculate and predict what the reaction rate, or reaction, so used to saying rates now, what the reaction equilibrium constant will be for the combined reaction. So if we have the reaction A reacting to form 2B, and that has an equilibrium constant of K equals 0.010, what is the equilibrium constant for the reaction B reacting to form 1/2 A? So I'm going to write this. So how do we need to manipulate this equation to be like, like this one? It's two things we have to do. Divide by 2, or multiply by 1/2. So then that'll give us the 1/2 A reacting to form B. And then what else do we have to do? Reverse it. So we just flip it. So for our K value, whoops, wait, redo. So for our K value then, this is going to be, right, so this K would equal 0.010. So if we multiplied all of our coefficients by 1/2, what do we have to do to K? Raise it to the 1/2 power. So this is going to be 0.010 raised to the 1/2, which is the same thing as the square root. And then for this one, let me do that. Okay, so now this is 0.1. So since we reverse the reaction, what do we do to K? You raise it to the -1, or you invert it. So we would say this K for the forward reaction, K for the reverse reaction would be 1 over those numbers. And that would give us B 1/2 A. So now K for this reaction is going to be 10. Yeah. So you kind of think of it, I mean, we're really applying all of these operations to the equilibrium expression, right? With the concentrations of A, concentrations of B, or products and reactants. But we can apply them straight to K without having to write out all of that stuff. So you kind of think of it as like 3 new operations for reaction math. Oh, I didn't clear this one. All right, so consider the following chemical equation, equilibrium constant at 25 degrees C, and calculate the equilibrium constant for the following reaction at 25 degrees C. It should take a couple minutes. Start working on that one. Because we only needed to get to slide 28 today. We're on 24 and it's been 15 minutes. Or not 15, 45 minutes-ish. So it's good. So you didn't necessarily have to do it in this order. Could have done the coefficient first. But I just flipped it first. So we do, right, the k raised to the -1. And then we multiply the whole thing by 2. And so we raise this to the second power. Ah, 2.1. Oh yeah, it's 2 sig figs. Yeah, and then, does anybody have any questions? Did you miss a step? Cool. Feeling easier so far than rates, kinetics? Yeah. Yeah, it is a much shorter chapter 2, which is why like the exam's only in a couple weeks. Oh yeah. Oh, and I forgot to mention the mechanism quiz will be next week, Tuesday. And then in my Canvas announcement, I posted everything that you need to be able to know how to do. Good on the slide now? Okay, so like I mentioned earlier, we can manipulate equations that we know K for. Oh boy, everybody's phone's about to go off. It's an Amber Alert. Oh, heat warning? I mean,
Conserve energy management, public health and safety.
fun. Surprised it's actually not warmer in here. Okay, so as I was saying though, we can manipulate equations or balanced chemical reactions that we know K values for to predict K values for new reactions. So if we can find reactions, and there are actually entire lists of known reactions under standard state conditions, we can use those, add them together, find new equations. So for this reaction up top, we want to figure out what K is. So the first step is to look at the equations that you're given and say, how do I make these add up to that equation? I think the easiest thing to do first is flip any of them that need to be flipped, right? Because then you're looking at stuff that's on the correct side. And then you can go from there, adding coefficients, or really multiplying by coefficients, to make all of the quantities line up. So do I need to flip either of our two given reactions? Yeah, the second one, right? Because this has carbon monoxide here. Then our third reaction has also carbon monoxide in the reactants. So if we added these together right now, we'd end up with 2 CO. And the reaction we're trying to add up to doesn't have carbon monoxide at all. So if we flip this reaction, we'll be able to cancel that out, and then also get water on the correct side, get CO2 on the correct side, and get hydrogen on the correct side. So I'm just going to rewrite that second one. CO2 plus H2, H2O plus carbon monoxide. And now our K value is going to be, it's going to be that K2 raised to the negative 1. 1 e to the 5, oh. Easy, 1.0 times 10 to the negative 5. So now we're not using this one anymore. What else do we have to do to make these add up correctly? Or is there anything else? Is there anything else I have to do? There's nothing else. We can add these together. Just wait for somebody to have the confidence to say it. It's okay to say it and be wrong. So now we just add these together. So if we adding our equations together, easy enough. Just look for anything that's on both sides, right, in the same quantity. So you have carbon monoxide and carbon monoxide. Get rid of those. Our hydrogens will add together, and so we'll get CO2 plus 3 hydrogen. Give us water, or let me do this in the same order. Methanol, CH3OH, plus water. And now our K1 is going to be equal to K2 times K3. Good? Right on. So we can also use K, calculate equilibrium expressions with pressures instead of concentration. Because for a gas, its partial pressure is related to, directly proportional to its concentration. So higher pressure, higher concentration, lower pressure, lower concentration. And we can plug those in and calculate Kp, which is the equilibrium expression for partial pressures, instead of Kc, which is the equilibrium constant or expression with concentrations. And notice here too that this is now PSO2, sulfur dioxide, and it's in parentheses and not in brackets. Because square brackets mean concentration in molarity. But all of the same rules apply. So if we want to flip it, we still raise that Kp to the negative 1. If we multiply the entire balanced chemical reaction by 2, then we raise Kp to the second power, or to the 1/2 power, what have you. I thought I cleared all these. Make sure I cleared the rest of these. Okay. So the value of Kc, though, is not exactly the same as using Kp. They're related, and we can actually derive that relationship just by understanding the units of molarity and how they relate to ideal gases. So our Kp, or our concentrations that we're using are molarity, capital M. And what is molarity? What are the units of molarity? Moles per liter. So for a gas, can we calculate really pretty easily what it is in moles per liter? Any particular equation come to mind? The ideal gas law? Yeah. PV equals nRT. So we can take the ideal gas law and solve it to get moles over volume, or N over V. And so we'll get P over RT equals N divided by V, bless you, where N is moles and V is in liters. And that gives us a way to convert between the two if we know what the temperature is. And very often you will be given the temperature because equilibrium constants are specific to different temperatures. Because if you remember, our rates and our rate constant is dependent on temperature. Right? Increasing the temperature will increase a rate, and then how much that rate increases, or how much K increases, is also dependent on the activation energy for a particular reaction. So in any given reaction where you've got two rates balancing each other, temperature is going to have a greater effect on one than the other most of the time. And that will change your equilibrium. All right, so I'm just going to go through this. And we can get from Kc to a pretty simple equation for Kp, but it's going to start out messy at first. So if our equation for Kc using concentrations is going to be A raised to the A, nope, sorry, products over reactants, C to the C times D raised to the D over A raised to the A times B raised to the B. We can now substitute out concentration of each of those things with the partial pressure divided by RT. And then it becomes the partial pressure of C over RT raised to the C times the partial pressure of D over RT raised to the D, partial pressure of A over RT raised to the A times the partial pressure of B, RT, B. It's like, okay, well, that's still pretty messy. Now, though, we can factor out the RT from each of these, right? Because they're both being divided by RT, but it'll be RT raised to the exponent of its respective partial pressure. And so we'll get, I'm going to move this way now, the partial pressure of C raised to the C times the partial pressure of D raised to the, I guess I don't need these anymore, partial pressure of D raised to the D over, times 1 over RT raised to the C plus D, partial pressure of A raised to the A times the partial pressure of B raised to the B times 1 over RT raised to the A plus B. Again, still not very neat. We can make this a little bit better again, though, by saying partial pressure of C, partial pressure of D, partial pressure of A, partial pressure of B, times 1 over RT raised to the C plus D minus the A plus B in parentheses. And you can even distribute that negative, which I kind of like a little better, because then it's C plus D minus A minus B. So I'm actually going to go ahead and do that. So minus A minus B. So if we have the partial pressure of each of these reactants and products We can actually convert that from Kp into Kc as long as we know the temperature. And there are also some special conditions now where Kc is equal to Kp. Because what happens if C plus D is equal to A minus B? So if that whole thing is 0, what is 1 over RT raised to the 0? It's just 1. So it disappears. So we have the same number of moles of gas in the reactants as we have moles of gas in the products. Kc and Kp are equal. So I can write this as now Kp times 1 over RT raised to the C plus D minus A minus B equals Kc. Or Kp is equal to Kc times RT raised to the C plus D minus A minus B. Sometimes it just works out nicely, as long as you're working with ideal gases and ideal dilute solutions. So you don't have to remember or memorize how to derive this. It might be useful if you can at least remember why it's derived this way, or why this equation relationship is what it is. Because if you can't remember specifically if it's this, then on the exam you could say, well, I can replace the concentrations with the partial pressure divided by RT, and then you can go through and you can derive the whole thing. Just a little bit of math. Does anybody need more time on this slide? All right. So we can also swap out that A plus B minus C, or sorry, C plus D minus A minus C with delta M. And so if the change in the coefficients is 0, then Kc is equal to Kp. Because that's what that C plus D minus A minus B, it's just the change in the coefficients of gas, specifically of gas. So for this equation, well, what is Kp for this temperature?
Same as Kc.
Why?
Because they're equal moles on each side.
Equal number of moles of gas on each side. So if we have, it ends up being our products, right? So we can calculate delta N is going to be our products minus our reactants. So minus 1 for the hydrogen, minus 1 for the iodine, delta N equals 0. So when delta N equals 0, then Kc is equal to Kp is equal to 6.2 times 10 to the second. So always check delta N first. Because you could go through and you could do this whole thing with all the numbers, and you'd have just a great time doing it. But you'd be kind of sad when you got to the end and realized, oh, maybe I didn't have to. So calculate delta N first. And remember, this only applies to gases. Right? So if we have a reaction that has gases in it, then calculate delta N, and you can convert Kc to Kp. So I haven't pointed this out, and maybe you hadn't even thought of it, but K is unitless. And without going really into any depth, it's a little bit hand-wavy, but it's because we're assuming that everything is ideal. That's basically the assumption that's happening. And so these Kc values are all relative to standard concentrations or standard pressures. And so we're actually taking each of our concentrations. So if this is 3.7 molar, we would be really doing it relative to a 1 molar solution. And so you divide each of the concentrations by 1 molar, so they become unitless, or the partial pressures by 1 atmosphere, and they become unitless. And so it's just 3.7. And that's why, even though we've got varying coefficients for these concentrations or partial pressures, it doesn't have any effect on the units of K, because there are none. Because even before those coefficients, they don't have units. And there are a lot of things that work very, very closely to ideal conditions. But at some point, those ideal conditions are not ideal. And you have to consider that other effects. If you want to know more about that, that concept is called activity. And it's the proportion of the concentration that you add that is actually able to participate in reactions. Because sometimes there will be other ion effects, and so it'll exclude some of those ions in solution from participating in the reaction. That's later stuff. I don't know if we'll probably talk about activity a little more later. But just for now, K is unitless. Oh, yeah. OK, so under which circumstances are Kp and Kc equal for the reaction shown here? Any other answers other than A? All right, yeah, it's A. Right, if the coefficients of the products, reactants are equal, Kc and Kp are the same. How much farther do I want to go? I think what we'll do now, because this is, like I said, already a good bit farther than we needed to get today. We can get an earlier start on the worksheet and exams. So I want to introduce this idea, and then we'll rehash it next week, or not next week, Thursday. Holidays got me all messed up. When you have, so up until now, we've been talking only about gases and aqueous species. And so even though I'm not writing any of the state labels on anything, they are important. Just doing it for brevity's sake. Because when you have sort of heterogeneous mixtures of things, the concentrations of solids and the concentrations of liquids don't change, practically speaking, right? Like we know that if you're looking at an absolute scale, yeah, it's going to change a little bit, but practically speaking, it's not changing. So if you have a solid or a pure liquid, those are actually left out of the equilibrium expression because the concentration doesn't change, and therefore it has no bearing on the equilibrium. So if we write out the equilibrium expression for the reaction between carbon dioxide and water, we're going to leave out water. So we'll get the concentration of H plus times the concentration of bicarbonate over the concentration of just CO2 gas. Because the concentration of pure water is 55.5 molar. And so if you react a tiny amount of CO2 with the water, it doesn't change. Because for all intents and purposes, it's so much more water. You're talking about water diluted in water, so its concentrations, yeah. Okay. That's where we'll leave it off for today.